Right, okay. So as usual, if you have anything, just pause and ask me questions, all right? Okay?
Okay.
Right, okay. Okay, so where was I? So I was talking about the polar method, right? The polar method for um, normal, or generating normal random variables, okay? Right, okay, so it goes like this, okay? So suppose you have X and Y, independent um, standard normal random variables, okay? Standard normal. Right? Basically, it means X is N01 and Y is also N01, okay? And they are independent. So suppose you take the following transformation, right? Okay. So basically, you have a pair of coordinates here. So this would be your angle. This will be your length, right? So basically the height here is given by r sine theta, and the base here is given by r cos theta, okay? So basically you also have a representation of x equals to r cos theta and y equals to r sine theta, okay? So as you can see, if you take the square, right? So you will get this form, okay? X squared plus y squared is equal to r squared cos theta plus r squared sine theta. But then you know that cos squared theta plus sine squared theta is equal to 1, right? It's a basic trigonometric identity. Okay. So once you have this, we look at the density, right? So the joint density is easy. So you just take the density from X multiplied by the density from Y, right? So that would give you something like this, okay? Right. Now, suppose we make a kind of a transformation, okay? So I'm going to erase something here. So I'm going to erase this. Okay, make some space. So suppose we make this transformation. D is equal to, sorry, this. Okay, D equals to x squared plus y squared. And theta equals to arctangent y of x, okay? So we want to find the density of d theta, okay? So this one we can obtain from standard theory, which is you take the determinant of the Jacobian, right? And multiply by, you make a transformation, right? For example, make a transformation of some transformation d theta. Okay. So basically then this part here we already have something like this. So here, right? So this thing here is equal to your D, right? So that would give you a E of minus D over 2 over 2 pi. And all that remains is finding the Jacobian, right? Okay. So by definition, your Jacobian is equal to for a two variable density. So you have the partial derivative of d over x, d over y, and then theta over x, theta over y. Okay. So you need to find this matrix of derivatives, and then you take the determinant, right? So this is the determinant. Okay. So let's work out the Jacobian, right? So your Jacobian is equal to this one. The first one is 2x. The second one is 2y, right? So theta over d of theta over dx. So you're differentiating the arctangent function. So basically you differentiate inside and multiply by the derivative of the arctangent. Okay, so differentiating with respect to x, you get minus y over x squared. That's over 1 plus y over x squared. Okay, so if you remember the derivative of the arctangent of the arctangent function is equal to 1 over 1 plus x squared, right? So it's related to the Cauchy density, okay? So this one is then, you have this one is 1 over x over 1 plus the following, okay? So the Jacobian is equal to 2 of this plus 2y squared x squared over this. So this is equal to 2, right? Okay, because this is basically multiplied by 1. So basically the numerator and the denominator cancel off each other, okay? Right, so basically you have a 2 here. Now over here, I will simplify this as follows. So note that your support for D is positive, right? Because D is always positive. Now over here, the support for theta, we will run it from 0 to pi over 2, right? Just for the positive values first. Okay, so over this domain, right? Sorry, over this support, you can check that f of d theta is actually a density. Okay, so let's check that, right? So I'm going to erase some of these things. Everyone can hear me, right?
Yes.
Okay, is it clear or is the reception okay?
Very clear.
Okay, that's good. Right, so we can check, right? Okay, just check. Do the double integral. So you do the double integral of so this whole thing here, right? Okay. So that's 1 over pi e of this d. That's a d, right? So actually, okay. So maybe I changed the notation slightly. Maybe d is not such a good notation. Maybe I use the bill. Okay. Same. dw, and this is d theta, okay? 0 until pi over 2. This will be 0 until infinity, right? So this to check, this should be E of this. Okay, so evaluating this part would give you a value of 2, it's 1 over pi, okay? So here is 2, right? So this is equal to basically 0 over 2 pi times 2 over pi, right? D theta, so this is 1, right? Okay. Now, actually, we don't want to restrict the theta to only just the first quadrant, right? We want to extend it over the entire 4 quadrants. So from 0 to 2 pi instead of 0 to pi over 2. So,
Sir, for the integral,
yeah.
How do we choose the bounds?
Sorry?
For the double integral, how do we choose the bounds? Just because we have the first quadrant, like from 0 to p.
Yes,
pi.
okay. That's a good question. Now the bounds here, right? The bound for your theta in this case is running from it. For this to be a density, right? It is running from 0 to pi over 2. Okay. Whereas for your W, it's clear, right? Because it's the sum of 2 positive numbers. Okay.
Okay, thank you.
Okay. So if this is not pi over 2, then you'll find that this is actually not a density. Okay. So your theta is running from 0 to pi over 2. But then we want to kind of like relax this a little bit, right? So we want it to run until preferably we want it to run until 2 pi, right? So basically we need to do some adjustment over here. So again, this one is equal to 2 times, this is d over 2 pi, right? Now, d is positive and your theta is between 0 to 2 pi, pi over 2. Now, if we move this to 2 pi, right? How should you change this density? So first you look at this more carefully. So this one, or maybe rather if you go back to here, right? If you change this to 2 pi, right? Then what should this be? If you change it to 2 pi, then this would be 2, this integral will be 2 over pi times 2 pi, right? So it'll be 4, right? So basically, that means you have to divide this thing here by 4. If you scale this pi over 2 to 2 pi, okay? So basically, it's something like this. Sorry, this is pi. Sorry. Okay, so basically, you are going from pi over 2, you scale up to 2 pi, right? So you're basically multiplying by 4. When you multiply by 4 on the uniform, right? So you will have to correspondingly scale back by a division of 1/4 to balance out, okay? So over here, you will divide by 4, okay? So you again So this is D is positive, and your theta is between 0 to pi over 2. So now you scale it to 2 pi. So here you divide by 4. So you will get this. So if you divide by a 4 here, so then you get 1 over 2. Pi. Okay. So 1 over 2 pi times 1 over. So maybe I should write like this. 2, 1 over 2 pi, right? Okay, once you have written it like this, right, then we can think of this as, we can think of this part as the uniform density. Okay, and this part here as the exponential density with parameter 1 over 2, right? And these are independent, okay, because you can write them as a product. All right. Okay, so far so good.
Yes.
Okay, so now we have this joint density. Okay, so basically now what happens is that we know that our R square and this is our okay, so they are independent. Okay, and this has an exponential 1 over 2 distribution, and this has a uniform 0 to pi, okay, distribution. Okay, so this gives us a recipe to perform the following generation. Okay, so we have step 1 here. So we generate U1 from 0, 1. Generate U2 from 0, 1. Okay, so we generate 2 uniform random variables. Then step 2. So we want to generate an exponential random variable. Okay, so we take so that's our R square, right? So R square is equal to minus 2 of log of U1. Okay, remember your inverse transform method, right? Your inverse transform for generating exponential lambda from the uniform is basically through this transformation. Okay, so this one I think we already covered it in the lecture and tutorial. Okay, through this transformation, where in this case this R is a uniform. So basically over here your parameter is your lambda is 1 over 2, so it comes up here. Okay, and then the other one is your theta here will be you want to generate 0, 2 pi uniform random variable. So basically, is you just scale, right? So 2 pi times u2. Okay. This is very easy. If you want to make uniform random variable, as long as you know how to make a uniform random variable within a 0-1 interval, you can transform it to any other uniform random variable by scaling. Okay, by scaling or translation, right? That means you add some constants to it. Okay. So once you have this, then your step 3 is complete. So you have a step 3. Right, so your r axis are r cos theta, right? Okay, so your r is a square root of -2 log of u1, and your theta is that, so you have cos 2 pi u2, okay? And your y is r sine theta, so that gives you this result. Okay. All right. So this is an alternative way for you to generate normal random variables using the polar method. Okay. It's maybe slightly more demanding in terms of your familiarity with mathematical statistics. Okay. All right. So, but then it's very easy to generate. Okay. It's a bit different from your von Neumann rejection method. Okay. In this case, you basically, if you want to generate 1,000 normal random variables, you just do 1,000 times, right? Because for every uniform random variable, you just make this transformation and you are done. Whereas if you use the rejection method, some of your candidate values, right, may be actually rejected. So you may actually, in order to generate 1,000 variables, you might actually need to try maybe like 2,000 times or more. Okay, so maybe okay, so that's one point to take note. But of course, this method also has some. It may actually be slowed down by this operation, right? When you take cosine, right? And sine, right? So these operations require some kind of computation, okay? All right, so this usually is evaluated using infinite series. So if you still remember the infinite series, so that there are quite a few terms if you want to get it to a certain degree of accuracy. So this may actually be a bit computationally expensive. Okay. Right. Okay. So we have looked at 2 ways to generate the normal random variables. Yeah. Any questions from the students? Any queries? Okay. So not yet, right? Okay. So so I will stop this recording now so that to separate it from the next part that I'm going to talk about. Okay. Okay, so now I'm going to just quickly go through the revision for generating discrete random variables, okay? Right. So so just as a revision, so we have looked at the first one is on generating Poisson random variables with parameter lambda, right? So this one is very straightforward. Okay, so basically you have Poisson probabilities, right? So basically it's this. Okay, so for each probability, you might think of actually putting them on a line like this. Okay, so this is 0, this is 1, right? So for example, the length for p of x equals to 0 may be here, and then followed by this is the length of p1, and so on, right? Okay, so suppose you choose a uniform random variable between 0, 1, all right? Let's say you choose it somewhere around, you got it somewhere around here, right? You got some value around here. So what happens is that first we will, so in order to determine, so this one hits the value of 1 here, right? Okay, so how do we decide? Okay, so the algorithm works like this. And in step 1, so basically you generate U, right? From 0, 1. In step 2, this is what we call the initialization step, right? You have to initialize the algorithm. Initialize the algorithm. So I equals to 0. So your P, so I'm going to denote this with small p. P is E of minus lambda. And F is equal to P, right? This is your cumulative probability. Okay. So step 3, right? So first you do a checking. If your U is less than your F, so for example, the first step is we're checking whether, so our U is inside our F. So initially our F is here. Okay, our F is this length, right? 0 to F. Okay, initially, right? At I equals to 0. Okay, this is length. If this is true, then you will just basically set your x is equal to I, right? That means you take the value of I here. So in this case, your I is equivalent to your x, okay? You set your x is equal to I, and then you stop, right? Otherwise, else, you go to step 4. In step 4, you do the updating, right? Your P is updated to be the following. This one comes from the recursion relation, okay? For example, your P of x equals to x plus 1. Okay, maybe I'll use I here. Okay, so basically this is just I plus 1 over I plus 1 factorial, okay? So this one you can write it as follows. By rewriting this, you get, right? Okay, so once you rewrite it like this, you will immediately see that this part here is your P of x I, okay, the previous one. So basically you can get the next probability by multiplying the previous probability with a constant lambda and also the index. Okay, this is how you do the updating. So basically, this is the updating, right? It means the new p is the previous p multiplied by lambda over 1 plus I. Okay, and then you also do your updating. Your f is now the previous f plus the new p, right? So basically, what happens is that now you, instead of your f being here, you have updated your f to be here, right? Because your f is now the previous f plus p, right? Okay. Once you updated this, then you increment your I, right? This is incrementing your I, okay? And then your step 5 is you return to step 3, right? You do the check-in, you do the checker, right? So that means then you check, right? So once you have done the updating, you check again. So now in this case, when you do the checking, right, you will find that this is, in this case, it will be true. So then you will set your x equals to 1, and then you stop, and then you go back to step 1, okay? So in this case, the first value that you generated is 1, all right? And then so on and so forth, okay? Then you are going to generate a sequence of numbers which will have a Poisson lambda distribution, okay? So basically for discrete is quite simple because basically it's just partitioning the 0, 1 interval to lengths, and then you just use a checker like this, okay? Just check, just initialize and then check whether your U is less than the cumulative F. If not, you update it and then keep on repeating this until you locate the I that where your U falls in that interval, okay? So once you understand this idea, you can also use it very easily on the binomial, right? Okay. So before we move on, is it okay with this explanation for Poisson?
Yes.
It's just curious. I think sometimes I get the students who have joined to come in again and asking to join. So is it because you kind of like got disconnected or something like that?
Yes.
Disconnected. Okay. Then I have to keep looking on the screen because yeah. Let's say you ask to come in again, but then sometimes I keep talking and then I didn't notice. Okay. Okay, so I'll clear this. Okay, let's look at another example, which is you generate the binomial. Okay. Random variables. Okay. So your binomial random variable is the following. And you have theta, right? So you have theta I 1 minus theta n minus I. Okay. And that's I equals to 0, 1, 2 until n, right? So again, first we look for the recursion relations, okay? So this will be n, I plus 1, theta I plus 1, n minus I minus 1, okay? So if you rewrite this, you have I factorial here, n minus I factorial times 1 over I plus 1. Let me see, that's Okay, that should be. Okay, maybe I do it a bit more slowly. So this would be I plus 1 and minus I minus 1. Okay. To divide by n factorial over I factorial. Sorry. So this one you can write it as n factorial over I factorial, right? So basically you take out your I plus 1 here, and here you want to make it as n minus I factorial, but then you are starting with n minus I minus 1 factorial, so you cancel it off with n minus I, right? So n minus I, cancel this off, you get your n minus I minus 1 factorial, okay? Then this part is your theta of I, 1 minus theta of n minus I, so times theta over 1 minus theta, right? Okay, so this part here gives you your previous binomial probability, right? So that's why you can express this as the previous binomial probability multiplied by n minus 1 over I plus 1 times theta over 1 minus theta. Okay? So usually we may actually express this as a constant C, right? No, I mean just this part, right? C. Okay, so you have this recurrence relation. Okay, so now we can, once we have established the recurrence relationship, we can actually go through the steps as we did for the Poisson. So again, is on the straight line here. Okay, 0, 1, right? So your binomial would basically just create partitions on this line, right? So this may be P x equals to 0. So sequentially, right? P x equals to 1 and so on, okay? So step 1 will be the following. So you generate a uniform 0, 1 random variable, okay? So maybe suppose, say you hit here, right? Okay. So step 2 is again the same thing. So you have to initialize. Okay. So your I is equal to 0. Your P is equal to 1 minus theta power of n. Right? You sub in everything, so you get 1 minus power of n. So of course your C is the constant, right? And this is your cumulative probability, right? Big F equals to P, right? Again, step 3 is the same. Check if your U is less than F. You set your X equals to I, right? And then stop. Else, you go to step 4. where you do the updating, right? Updating will be your P will be updated as using the recurrence relation. So you will have the previous P times N minus I plus 1 times C, right? And then your F will be updated as the previous F plus the new P, and your I is updated as I equals to I plus 1. Okay, and then of course your step 5 will be you return to 3. Okay. Right, okay. So that completes the generation for binomial as well, right? So later in the tutorial, which I will upload to Spectrum later today, you'll get some exercises on using R to generate, all right? To generate Poisson and this binomial, okay? Random variables. And then you will compare it against the those generated using the built-in functions. All right, you should see that they are actually similar. Okay. Right. Okay. So this is all I want to talk about for this hour. For the theory, right? So we kind of like warm up a bit by revising and what we have learned, and also just added a bit of new things on the generation of normal random variables, okay? So next week, I'm going to go to variance reduction methods, right? So variance reduction methods will be some kind of methods that you use to reduce, for example, when you are trying to estimate certain integrals, okay? So there are ways to reduce the variance of the Monte Carlo estimates that come out from this methods, right? So of course you want Monte Carlo estimates that have smaller variance, because then the uncertainty is less, right? So next week we're going to talk about that. Okay. So okay, so I'm going to stop the recording now. Yeah.